force on a current-carrying conductor in a magnetic field. Electric current flowing through a conductor produces a magnetic field. The field so produced exerts a force on a magnet placed in the vicinity of the conductor. French scientist André-Marie Ampère, 1775 to 1836, suggested that the magnet must also exert an equal and opposite force on the current-carrying conductor. In the above activity, it is seen that the rod is displaced, which suggests that force is exerted on the current-carrying aluminium rod when placed in the magnetic field. The direction of force depends on the direction of the current and the direction of magnetic field. The displacement of the rod is maximum when the direction of the current is at right angles to the direction of magnetic field. Let us learn Fleming's left-hand rule. Stretch the forefinger, the central finger, and the thumb of your left hand mutually perpendicular to each other. If the forefinger shows the direction of the field and the central finger shows the direction of the current, then the thumb will point towards the direction of the motion of the conductor. Current is a flow of charge. This means that moving charges in a magnetic field would experience a force. This property is used to accelerate charged particles to very high energies. These high energies of the particles are used to study structure of the matter. Let us learn about the electric motor. A device which converts electrical energy into mechanical energy is called an electric motor. Principle: electric motors work on the principle that a current-carrying conductor placed in a magnetic field experiences a force. Construction: armature coil. A large number of turns of insulated copper wire wound on iron core in rectangular shape forms an armature coil ABCD as shown. Strong magnet. The armature coil is placed in between two pole pieces, N and S, of a strong magnet. This provides a strong magnetic field. Split ring commutator. It consists of two halves R1 and R2 of a metallic ring. The ends of the armature coil are connected to these rings. Commutator reverses the direction of current in the armature coil. Brushes. Two carbon brushes, B1 and B2, are used to press the commutator. Battery. The battery supplies the current to the armature coil. Working of the electric motor. When current is passed through the coil ABCD, arms AB and CD experience force. According to Fleming's left-hand rule, the force experienced by arm AB is in the downward direction and arm CD in the upward direction. Both these forces are equal and opposite. This force rotates the coil in clockwise direction until the coil is vertical. At this position, the contact between commutator and brushes break, so the supply to the coil is cut off. Thus, no force acts on the coil, but the coil does not stop due to inertia. It goes on rotating until the commutator again comes in contact with the brushes B1 and B2. Again, the current starts passing through coil and the arm AB rotates through 90 degrees, 180 degrees, 270 degrees and 360 degrees. Now the force acting on arm AB is downward and CD is upward. Again, this force moves the coil in clockwise direction. Thus, the coil rotates with the help of electrical energy. The coil of DC motor continues to rotate in the same direction. Uses of DC motor. 1. These motors are used in domestic appliances like mixers, blenders, refrigerators and washing machines. 2. These motors are used in electric fans, hair dryers, record players, tape recorders and blowers. 3. These motors are used in electric cars, rolling mills, electric cranes, electric lifts and electric trains. Magnetic levitation trains do not run on rails but float above them. A current passes through the electromagnets in the track and on the train. The magnetism produced lifts the train upwards. Try this out. Take a coil AB having 10 to 15 turns. Connect the two ends of the coil to the galvanometer. Take a strong bar magnet. Move the north pole of the magnet towards the B end of the coil. Observe the deflection in the galvanometer. Note the direction of the deflection, that is, right or left. Now repeat this with the south pole. Again observe the deflection. Note its direction. What will happen if instead of magnet a coil is moved? If both coil and magnet are kept stationary, do you observe any deflection? No, deflection is not observed. Let us perform one more activity. Take two coils of about 50 turns. Insert them over a non-conducting cylindrical roll as shown. Thick paper roll can be used. Connect coil 1 to a battery with a plug key. Connect coil 2 to a galvanometer. Plug the key and observe the deflection in the galvanometer. Unplug the key and again observe the deflection. No deflection can be seen in the galvanometer.